Welcome to YieldWise, the batch intelligence solution built on the mcube platform. By combining live batch data with a digital twin of the process, YieldWise predicts the yield impact of corrective actions in real time, helping teams make faster, more informed decisions. Let's take a look at how it works. This is the Explore view, the fleet-level picture. Every active batch in your facility is listed here. On the top right of each card, you can see the status chips. Green for on track, amber for at risk, and red for an active deviation. The key design principle here is risk stratification. The platform continuously monitors every running batch and surfaces the one that needs attention before your scientists have to go looking for them. Let's take a look at a batch flagged as amber at risk. This is a CHO-fed batch mid-run and the predicted titer is already sitting below the target. Crucially, no deviation has been raised yet. That is exactly the scenario this tool is built for. Let's take a closer look. This is the batch workspace. The header is designed to provide a complete operational snapshot in a single view, eliminating the need to scroll or navigate elsewhere. Three key KPIs are presented prominently: the predicted final titer, the process target, and the gap between them. The status indicator mirrors the Explore view, ensuring a consistent understanding of the batch's current state. The header also displays the number of days remaining in the production window. This metric provides critical context for decision-making throughout the batch lifecycle, as remaining time is one of the most important resources being managed. The titer trajectory chart overlays three perspectives: the actual batch trajectory, the historical average, and the target outcome. Together, these views show where the batch is today, how it compares with historical performance, and where it needs to finish. The gold curve represents the historical average derived from previously completed batches of the same process. It serves as a performance benchmark built from real process history, capturing the expected growth phase, peak production period, and maturation through harvest. In this example, the batch initially tracks closely with the historical average before beginning to diverge. This divergence is the early warning signal identified by the platform. The visualization makes emerging risk immediately apparent in a way that tabular data often cannot. Below the chart is the batch events feed. This feed serves as the complete audit trail for the batch. Milestones, feed additions, cell density measurements, and system-generated events are captured automatically. When a batch begins to drift from its expected trajectory, this timeline provides the context needed to understand what occurred and when. On the right is the predicted final yield panel. This panel presents the model's current best estimate of the final batch outcome, continuously updated as new process data becomes available. Beneath the headline prediction is the forecast confidence range, showing the lower and upper bounds associated with the estimate. The accompanying visualization displays the projected trajectory against the target line, along with a shaded uncertainty band. A narrow band indicates high model confidence, while a wider band reflects greater process variability at the current stage of the run. Every forecast displayed here is dynamic. Rather than relying on a static calculation, the model continuously ingests new sensor data and updates its predictions in real time. Below the forecast panel is the forecast horizon control. By default, projections extend to the planned end of the batch run. The forecast window can be adjusted to evaluate alternative scenarios, such as an early harvest strategy or a modified production schedule. As the horizon changes, the forecast updates immediately, allowing rapid assessment of how confidence and expected yield evolve over time. The yield drivers panel sits directly below. This view answers a critical question. Among all variables influencing the batch, which ones are having the greatest impact on predicted yield? The chart ranks process drivers by both magnitude and direction. Positive contributions are shown as factors increasing expected yield, while negative contributions represent factors reducing expected performance. These attributions are generated automatically using the same machine learning model that powers the yield forecast. For this batch, the primary negative driver is a glucose-related parameter, which aligns closely with observations in the critical process parameter monitor. This connection between yield drivers and process conditions is intentional. It provides a direct link between root cause identification and potential corrective action, helping teams focus interventions where they are most likely to improve outcomes. Below the main panels is the CPP monitor, the process parameters section. Every critical process parameter for this batch is shown together in a single view. Each card shows the parameter name, the current value, the normal operating range, and a sparkline of the recent trend. The status chip is color-coded. Green means within the normal operating range. Amber means trending toward the boundary. Red indicates that the parameter has breached the normal operating range. Below the CPP monitor is the Simulate panel, the digital twin what-if simulator. This is where YieldWise moves from diagnosis to corrective action. The panel header displays the key context, batch status, days remaining, and the current yield gap. Below it, an amber alert banner flags the specific parameters that are outside the normal operating range and explicitly invites corrective scenario modeling. The expectation is that every batch review includes a what-if step. That is how deviations are prevented rather than responded to. On the left of the simulator are the CPP controls, one for each controllable process parameter. The sliders are not just inputs. Each one has 3 color zones built into the track. Green is the normal operating range. Operation within this range requires no additional documentation. Amber is the proven acceptable range. Operation within this range is permitted, but the platform requires change control documentation before the scenario can be staged. Red is outside the proven acceptable range. The system blocks staging entirely. The zones make the risk of any proposed change visible before any action is taken. In this example, the glucose level is adjusted. Notice how the other parameters update automatically. This is the CPP cascade. Process parameters in a bioreactor are not independent. Changing one affects others through well-established physiological relationships. The digital twin models these interdependencies and propagates them automatically, ensuring that scientists always see a physiologically consistent set of conditions rather than a single isolated parameter change. Every auto-adjusted value is clearly labeled. Any of them can be overridden manually. The scientist remains in control. The model provides a biologically grounded starting point for scenario evaluation. On the right side of the simulator, 2 yield readouts update in real time as process parameters are adjusted. The simulated projected titer is the model's estimate of where the batch ends up under the CPP conditions that have been defined. Alongside it is the current prediction, fixed at the baseline value if no changes are made. The delta badge between them shows the simulated gain. The chart below plots both trajectories together. The do-nothing path as a solid line and the simulated correction path as a dashed line. Against the target reference, the simulated trajectory can be seen closing the gap. Below the readouts is the zone status banner. When all levers remain within the normal operating range, it displays a green confirmation that no change control is required. This is a meaningful output. It indicates that the correction can be actioned immediately without triggering the change control process. If one of the levers is moved into the proven acceptable range, the banner shifts to amber and flags that change control documentation will be required. In the red zone, staging is blocked. The platform enforces the process hierarchy. Once the scientist is satisfied with the scenario, the parameters are correctly positioned, the projected yield is acceptable, and everything is within the appropriate range, the scenario is staged for QA review. Notice that the button label includes the projected yield. There is no ambiguity about what is being submitted. The proposed outcome is part of the action. The simulator then transitions into the QA pending state. The header confirms that the scenario has been sent. An amber pending QA approval chip makes the status unambiguous. The parameter table below shows every CPP value that was part of the scenario, including the original value, proposed value, and the zone in which each falls. That is the record received by the QA reviewer. The reviewer can evaluate exactly what has changed and what the projected yield impact is without needing to rerun anything. Nothing is committed to the batch record until QA approval is granted. If revisions are required before approval, the modify scenario action returns the workflow to the simulation view. The full workflow is captured and traceable from the moment the scenario is staged. This completes the end-to-end workflow.